Chemsters, this is Mrs. Vandelay bringing you another version of Chemster video. So here we are, we're still doing chapter 14, which is your acids and bases chapter. And we just got done naming them, reviewing how to name acids. And so now we're going to talk about, well, what is an acid and what is a base? How do we define them? So we start off with Arrhenius. There is a chemist, a very well-known chemist for his time, a man named Svante Arrhenius. He was a Swedish chemist, yeah. And anyway, he actually did his original work looking at solutions that conduct electricity. So if you remember that lab that we just did, our intro lab to this unit, certain solutions lit up that conductivity meter, right? Well, look at the time frame. It was 1887. So this is a really exciting time in chemistry and physics because electricity and batteries were just coming into play here. So it was a very exciting, people were very interested in this very unusual thing of electricity. And so he was actually looking at solutions that conduct electricity. And do you recall from our previous lab that, well, did our acids conduct electricity? Well, yes, they did. Did our bases conduct electricity? Well, yes, they did. So he actually looked at these solutions and he categorized them. And so he said, oh, these solutions that conduct electricity that contain H+, I'm going to call them acids. And so here are some examples: hydrochloric acid, nitric acid, chlorous acid. And then he said, I'm going to call these solutions that conducted electricity bases, and they contain hydroxide, sodium hydroxide, potassium hydroxide, and there's others too. All right. So he just defined these as, well, acids contain an H+, not just any old H's, but H+, and bases contain the hydroxide ion. All right. And so there's a little problem with his base definition. Didn't we say earlier, I think it was on the front page of your note packet, that baking soda is a base and ammonia is a base? And the problem is they don't contain hydroxide. Now what do we do? All right. Well, there has to be a better definition. And two chemists, Johannes Bronsted, he's actually from Denmark, and Thomas Lowry, he's from Great Britain, they didn't really know each other. They didn't work with each other. But around the same time period, all right, within probably a year of each other, they both came up with a new definition that is better than the Arrhenius definition, is more comprehensive than the Arrhenius definition. And instead of saying that acids just have an H+, now we say acids are going to donate an H+, or lose an H+, and bases are going to accept an H+. And this is crazy because now this will allow baking soda and ammonia to act like a base. So let's see what I'm talking about here. So what I would do first is look at my materials here. What two things, one on the left side, one on the right side, well, you know, reactants and products, what kind of looks alike? What are they very, very similar to? And I'm going to put brackets around them, and I highly recommend you do the same. Doesn't NH3 and NH4 kind of look alike? Well, what's the difference? This has NH3, this has 3 hydrogens, this is NH4, this is 4 hydrogens and a plus. So what can I say ammonia did? Ammonia gained an H+. Oh, all right, so if it gained an H+, and look at the definition, ammonia must be a base. And didn't we already say that? Well, what I would do also is do the same bracket. I would say, well, how are these two related? Aren't they very similar? Sure. This has one H, this has no H. This is neutral, this is negative. So what happened? It actually, you know, lost or loses an H+. So what's our definition? What loses what loses an H+? Well, acids do. All right, so HCl is an acid. Well, I knew that. Well, very good. It still lost an H+, okay? So this Bronsted-Lowry definition is really going to be our working definition. We're going to pay, you know, from here on out, our attention to this definition. Make sure you know it. Now, there's a few more terminologies here I want you to know. A conjugate acid is a particle formed when a base gains an H+, all right? So, oops, sorry about that. What does that mean? That, I'm going to pause. So let's look at the example up here. So how am I going to talk about conjugate acid, conjugate base? So the conjugate acid is the particle formed. It is a product. So when we talk about conjugate acids and conjugate bases, they can only be on the product side. The true acid and true base are the reactants. The conjugates are always on the product. So a conjugate acid is a particle formed when the base gains an H+. So if this is my base, well, what did I bracket? I bracketed this. That must be my conjugate acid. So here is NH3, here's NH4+. This gained the H+, so it's my conjugate acid. So what do you think the chloride is going to be? Well, it is the conjugate base, the particle that remains after the acid donated. So if I take away the H+, I'm left with the Cl-. That is my conjugate base, all right? So a conjugate acid, conjugate base pair are on the product side. Maybe you want to write that down. And it consists of two substances related by the loss or the gain of a single H+. Okay, so this gained it, this lost it. Okay, so in sample D, let's go ahead and look at these, and we're going to figure out which is my acid, my base, my conjugate acid, my conjugate base. So let's do that, okay? Really, to do this is pretty easy. If you just identify one of the species, everything falls into place. So here's NH3, and what is its partner? What does it kind of look like? What separates its formula by an extra H or a loss of an H? Well, I think you're going to see this, that it is an H4+. Here's my bracket. All right, see how this goes from 3 H's to 4 H's? So what do we want to say it did? It gained an H+, right? So what did we define? Look above. What gains an H+? We decided that is its base, right? All right, so what's at the other side of the bracket? It's its conjugate acid. So now what? Well, let's look at the bracket here. Does that make sense? Should they be bracketed? H2O and OH-. Well, how did H2O become OH-? H2O did what? Lost an H+. Well, what's our definition of that? It's an acid, so its partner over here is its conjugate base. See how I did that? Okay, let's try the next one. Here's HCl. I would just start from the first one. And on the other side of the arrow, all right, what is its partner? Okay, well, let's look over here. It is definitely Cl-, isn't it? Here I have HCl and here I have Cl-. So what did HCl do? Oh, it lost an H+. Here I have one H. Here I have no H's. All right, it lost. So what loses? What's a loser? Oh, acids are losers. Okay, and so now what? Well, how am I? I'm going to just bracket these two things. All right. And so if H2O and H3O+, well, what did H2O do? It gained an H+. It went from 2 to 3. It went from neutral to positive. So what do I call anything that gains? That's my base. It's all about that base, folks. All right, so now what? This is the conjugate acid, and this is the conjugate base. So right now it looks like, well, you always write the conjugate acid first and the conjugate base last. It makes no difference. The order makes no difference. Just the acid and base, whichever order you want to do it, are going to be on the reactant side. The conjugate acid, conjugate base will always be on the product side. So why don't you, I've done 2 of them for you. Why don't you work on the next 2, all right, and stop, and then come back and see how you did, okay? How's that for a plan? Pause this. Do 3 and 4 and come back. All right, welcome back. See how you did. So the first thing I did is took H2SO4, found its partner. It's HSO4-. So what happened? I have 2 hydrogens. I have 1 hydrogen. It lost an H, therefore it's an acid. This is a conjugate base. Then I bracketed the other 2 things that are remaining, H2O and H3O+. Well, what's the difference here? I have 2 hydrogens, I have 3 hydrogens, I gained. Neutral going to positive, it gained an H+. So what gains? Bases. There's my conjugate acid. So once again, you did not have to necessarily, if you have water and water, you could have made these 2 pair up if you would, and then these 2 pair up. So it really doesn't make any difference if you have water and water, all right? So what I did is I just kind of worked backward. If this is my conjugate acid, whichever water I paired it with will have to be the base. I made this my base, okay? So that whichever one it paired up with will be my acid, okay? Now, what's different about the next two? Oh, there's no products, all right? So how are we going to deal with those? Okay, well, let's find out. All right, so here I have two reactants and no products. What am I going to do? Well, look at this closely. You can name that, can't you? How do you name this? Oh, nitric acid. It's an acid, isn't it? Oh, it's an acid. So if it's an acid, what do acids do? All right, acids are going to, lose an H plus. So take the formula, take away an H. What are you left with? NO3. This is neutral. Take away a plus. What is 0 minus a positive? A negative. Oh, okay, so what does that make this? The conjugate base. Oh, over here. Okay, so now what? Well, if this is my acid, then what's water going to be? It can only be a what? It's all about that base, all right? So then what am I going to make? I'm going to make a conjugate acid. So what does a base do? Base is going to gain an H plus. So take H2O and add a what? Add the hydrogen. So now I have 3 hydrogens. It's neutral. Add a positive. What's 0 plus 1 is plus 1. That's my charge. All right, so I make H3O positive. Now something to kind of look at, I don't know if you've noticed this yet, but nitric acid is neutral. There's no charge. Water is neutral, no charge. Well, this is a negative and this is a positive. If I were to add those up, isn't that also equal neutral? So each side has to have the same charge. So the left-hand side or the reactant side has to be the same charge as the product side. So neutral plus neutral is neutral. Negative and a positive is also neutral. So that makes sense. And look through some of these past ones, it should work. So this better work for this one. Now, here's water. Water can act as an acid or a base. Look right here. Here water is an acid, here water is a base. So I don't know what to do with water. So it really is going to depend on what it's paired with. All right. So what do you notice about carbonate? Is there a hydrogen? No. Can it be an acid? There is no hydrogen to lose. So if it's not a hydrogen or not an acid, it must be a base. And what do bases do? Well, bases gain an H plus. So what am I going to do? Take this, put an H out in front, and what is a plus from the H plus and a minus 2? Well, what's a plus 1 minus 2? Well, I hope you know it's a -1. So that would be its formula is a HCO3 negative bicarbonate. Ooh, and what is this? This is a conjugate acid, okay? So now what? Well, water then must be the acid. And what do all acids do? All acids are going to lose an H plus. So I have 2 hydrogens. Take away a hydrogen, I have 1 hydrogen. Take neutral, -1 is going to be a negative, OH minus, and that's going to be my conjugate base. And remember what I said about the charges? What's -2 plus 0? -2. What's -1 plus -1? Oh, -2. So each side is equal. Okay, and I believe the next page is now we're going to talk about the differences between strong and weak acids. All right, so let's turn the page. Oh, there's another objective before we talk about strong and weak acids. All right, so I can describe the hydronium ion and the concept of amphoterism. What a mouthful, all right? So it says sometimes water will accept the hydrogen ion. Other times it donates a hydrogen ion. A substance that can act both as an acid and a base is amphoteric. So it says, what substance above acts like an acid then a base? Well, let's look over on the prior page, okay? Let's do that. Scroll down a little bit. Okay, so what acts both as an acid and a base? Well, look at that. We have water is an acid, water is a base, water is a base, water is an acid. Water is a base, water is an acid, all right? So that's what we mean. And I kind of alluded to that earlier when I had said that, if I just look at water, I can't tell what it's going to do. I have to look at what it's with in order to know if acid is going to be an acid or a base, okay? So what substance acts like an acid, and then a base would be water. There's some other ones too, all right, like bicarbonate can act as an acid or it can act like a base. Now, if you remember that, we said bicarbonate is a base, but if it's with a stronger base, it could act like an acid, all right? So that's the idea of amphoteric, okay? So now what? Let's talk about the characteristics of strong and weak acids and bases and identify common examples of both. All right, and then the second part is we're going to talk about percent ionization, Ka, Kb, and explain how they relate. So let's talk about strong and weak acids to start with. All right, so there are only 6 strong acids. All right, so there are only 6 strong acids. You need to what? Memorize these. Mrs. Vanderlei calls them the big 6, all right? So if I refer to the big 6, these are your strong acids. This comes into play in much more greater detail in AP Chemistry if you're going to take AP Chemistry. So you're going to hear me call them again, the big 6, okay? So what are the big 6? Can you do me a favor and fill out these 6 names? You know them. You don't need me to tell you how to do this again. You know, my Sprite is delicious. You know, I ate something icky and my ride has hydraulics. So go ahead and name these, and when you're done, come back. All right, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. So those are the big 6. You probably have heard of hydrochloric, nitric, and sulfuric as, you know, very common acids that we have used, but there are a total of 6 of them. And I said memorize these, all right? Know these are your big 6. So if I give you, oh, let me think, how about hydrocyanic acid? Is it on my list? No, it's not. It's not a strong acid, therefore it must be a weak acid, all right? So every other acid except for those 6 are going to be weak. So why do we care? Well, let's look down and find out. All right, so strong acids are what? Completely. What does completely mean? 100%. Each and every one of these HCl's are going to do what? Split up, all right? It's going to make a Cl minus and an HCl plus, all right? Or excuse me, H3O plus. And what I say, notice the what? Single arrow. That's also a clue. If it's a strong acid, you need a single arrow, okay? And so how does this look? I like to visualize things, okay? So let's picture what's going on. So if I pour some HCl into this container here, I guess my field of vision is a little bit smaller here. So what happens? It 100% dissociates. So if I put one HCl in here, well, guess what? It's going to split up. What if I put another HCl in here? Well, guess what? It's going to split up. What if I put another one in there? Well, guess what? It's going to split up. All right. There is no HCl molecules in this container. It's only the ions. Okay. So let's look at what a weak acid will do. Let's say all other acids are weak. Did I just say that? So this name, there's only a few of them. Oh, there's many, 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 many more. All right. So do me a favor. Number 1, that's a typo. There's no such thing as H3CO3. It's H2CO3. Can you go ahead and name these for me? Take a few minutes out. All right. Hopefully you pause this and then you, went ahead and named this. You're practicing this again. So this is carbonic acid, nitrous acid, phosphoric acid, hydrofluoric acid, and acetic acid. Now, what do you notice about acetic acid? There's no H in the front. The H is in the back. Well, it's an organic acid. Oh, wait, I teach organic chemistry. I know these things, okay? So it's an organic acid, and the COOH, all right, you should keep it together, all right? It is a C double bond OOH. It's called a carboxylic acid functional group, all right? And usually the H then stays with the OOH, okay? If you, by accident, make it HCH3COO, whatever, okay? But the proper way, the structural way to do this is put the H in the back, okay? Just a little something for you. So what do you know about weak acids? Well, strong acids, 100%, every single one of them split up. Well, guess what a weak acid does? It doesn't 100% split up. Some do, some don't, okay? And how do you recognize a weak acid then? Oh, look at this. This is a double arrow. More often than not, you'll probably see it written as something like this, an arrow going this way and an arrow underneath it, all right? That will also do it, but I couldn't type that out. Sorry about that. But this double arrow is the same as this double arrow. So what will my picture look like? So here is my hydrofluoric acid. I put it in a beaker of water, and what's going to happen? Well, maybe some of them split up, but do all of them split up? No, this one stays put. This one will split up. Oh, this one does not. Oh, let's try this one. This one splits up. All right, and so the question now is, well, how do you know how many of them are going to split up and how many are going to stay put? That's a great question. I'm so glad you asked that. So the point is, what is the degree in which the HF is going to split up? How many HFs are actually going to split up? How many of them will stay together? And that's what this next section is going to tell us. So comparing the strength of the weak acid, the greater the dissociation, the greater the split up, the stronger the acid. So in other words, the more H's that are in solution, the stronger the acid, because that's what makes the acid. That's what Bronsted-Lowry says. It's going to donate the H+. So the more that you donate the H+, the stronger it is. So the more it splits up, the stronger it is. That's what dissociation means, to split up. So how do I know? Well, a way to measure the amount of H+ is looking at the acid dissociation constant called a Ka. It's a numerical value. Every single acid, and I don't want to get into how, take AP chemistry and you'll learn the how, but how did these Ka values come up? It's a way to measure how much it splits up. So the larger the Ka value, the stronger the acid, the more it dissociates. The smaller the Ka, the less it dissociates. It's the weaker acid, okay? So on the next page, so here are the different acids and their ions. Some of them are called diprotic acids because I can have the first one and then the second one. Notice the formula of this oxalic acid has two hydrogens that can come off of. And then if I take one off, I have a second ion, the oxalate ion, that can still take off a hydrogen. Notice that phosphoric acid has three of these because we start off with H3PO4. We're going to have three of them that fall off. Methanoic acid, benzoic acid, ethanoic acid, they all are monoprotic. That means they have only one hydrogen is going to come off. And then over here is carbonic, it's a diprotic acid because it's H2CO3. And so here are the Ka values, okay? So this is a measure of how strong and how weak these acids are. So the bigger the number, the stronger the acid. The smaller the number, the weaker the acid. So just to practice a little bit, this hopefully is not too redundant for you, but how do I know which number is bigger? Well, I'm glad you asked. So when looking at these numbers, which number is bigger, your first place you look is the exponent. So which is a bigger exponent, 10 to the -2 or 10 to the -4? This is 1/100th, this is 1/10,000th. All right, so which is a bigger, 100th or a 10,000th? All right, hopefully you know that the 100th is actually bigger than the 10,000th, so this number is, okay? But what happens if your exponent is identical? So this is 10 to the -5th, this is 10 to the -5th. So now you look at the numbers out in front, the coefficients. Well, which is a bigger number, 6.3 or 1.8? Hopefully you know that 6.3 is bigger, so once again, that is the bigger number. So if your Ka value is this versus this is your stronger acid. If your Ka value is this versus this is a stronger acid, okay? So let's look at the chart now. So which of the weak acids, they're all weak acids, above will dissociate or ionize to the greatest extent. So what are we looking at to answer the question? Well, of all these values here, which Ka is the biggest? Well, look. Did you find it? It was the top number, wasn't it? All right, so the oxalic acid is the biggest value, has the greatest Ka, so it's going to be the strongest acid. What does that mean? It's going to split up the most. So if I put this in water, I'm going to have more H pluses and oxalate minuses than I would the oxalic acid that stays together. So which of the weak acids remain mostly unionized? Which one stays together the most? All right. Well, what are you looking for? The smaller the Ka. So which of these values has the smallest number? Well, it looks like this number is right here. All right, and what does that relate to? This. So your reactant is HPO42 minus, all right, and that is going to be the weakest acid. Why? Because it remains the most unionized. So if I put this hydrogen phosphate, that's what HPO4 is. If I put hydrogen phosphate into water, it's going to mostly stay as hydrogen phosphate. It's going to make very little phosphate ions and H pluses. All right. So the question is, well, look at this chart again. What's missing from this chart? What doesn't occur on this chart? None of the big six. Look at that. None of my strong acids are in this chart. All right. So why are they not on the list? Well, guess what? Their Ka values don't exist. Oh, really? Well, like I said, if you want to learn more about how these numbers are found to be, how they calculate these numbers, take AP Chemistry. I'll tell you all about it. All right. I'm going to give you a clue right now. Why is it on the list? Because each one of those six has an infinite Ka. And how big is infinite? Well, it's huge, isn't it? Infinity and beyond. It's huge. It's a huge, 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 huge number. So what does that tell you? All of it dissociates. 100% of it dissociates. I have all of it dissociating, all right? It's a huge number. So that's what that means. So, we aren't going to be talking about strong bases and weak bases. Your strong bases are going to be your group 1 hydroxides because they dissolve the best. Your group 2, your magnesium hydroxide, your calcium hydroxide don't dissolve really well, so they're not going to form as many hydroxide ions. How can you tell if it's a weak base, like bicarbonate and ammonia? Which one is a stronger base? You're going to look at their Kb values. I don't have that for you, but in case you're wondering, you'd do the same exact thing for a base. Well, I am done with what I wanted to accomplish. So, hey, don't wait to be great. We'll see you next time. Bye-bye.